In this lesson, let us learn how and when to apply the geometric mean. The geometric mean is the appropriate mean to use when you want to average ratios, percentages, index values, or growth rates. The geometric mean of n different numbers is computed as the nth root of the product of the n different values. So the nth root of x1 times x2 times all the way up to xn, where x sub 1, sub 2 are your different x values. To see the application of the geometric mean when we apply it to these scenarios, let us work out the following example. Suppose we say this is a variable. It could be the stock index, it could be enrollment at a community college, it could be income. The variable could be anything. Let us say this particular variable increases at a growth rate of 3% in 1 year, in the first year. Let us say it grows by 5% in the second year and 9% in the third year. So these are three different growth rates in 3 years. Our task is to find out what the average growth rate is over this 3-year period. Observe that you will not use the arithmetic mean. You will not add 3, 5 and 9 and divide it by 3. An extreme example in class would have explained that. To find the correct growth rate, here is how you want to proceed with the thinking. Suppose we start with an initial value of $1. The variable may be anything, but it helps to start with $1, and you will soon see why. We start with $1. A growth rate of 3% in the first year means the original value becomes 1.03 times what it was. So by the end of the first year, our dollar is now worth 1.03. So the second year starts with a value of 1.03, and then it grows by 5% again, so it becomes 1.05 times what it was. It was 1.03 initially. By the end of the year, it has become 1.03 times 1.05. And then in the third year, this is the starting value. It grows by 9%, so again it times 1.09. This, for our reference, is the compound value. I'll just write this in shorthand. This is the compound value of our $1 at the end of 3 years. Our task is to find the average value over the 3-year period. Now when we compute average value, this is where we will apply the concept of the geometric mean. Compare the formula I have written above and what we have here. Observe the x1 times x2 times xn. These are really the equivalent of those. 1.03 times 1.05 times 1.09. We had 3 different values, so n is 3. So the average value of our $1 in any one of these years over the 3-year period is the cube root of 1.03 times 1.05 times 1.09. Once I have written this out, then we will use our calculator to figure out the average value. You do not want to write out the compound value rounded off to 2 decimal places and then do a cube root. Let's get our calculator now to do 1.03 times 1.05 times 1.09. You should have 1.178835. We are not going to round this off. We just say this needs to be raised to an exponent of, within parenthesis, 1 divided by 3. An exponent of 1/3 is a cube root. Let us record 4 decimal places here. We have 1.0564. 1.0564. The interpretation of this number is, on an average, our dollar was worth 1.0564 in each of these years. So if our dollar has grown to 1.0564, then it means the growth in our dollar is 1.0564 minus the $1. You can think of it as I had initially invested my $1. That's not growth. So now I take my dollar off and I see that the amount of growth is 0.0564. Growth rates are always mentioned as a percentage. So instead of growth amount, I now need the growth rate. Need to translate this into a percent by multiplying by 100. And as you probably know, if you multiply by 100, the decimal moves 2 places to the right. So the average growth rate is 5.64%. Two things to note before we move on to its second example. I had mentioned here we would like 4 decimal places. That's because we sort of preempted or anticipated that by the time we come to growth rate, we will need 2 decimal places here. Do not round off growth rates to integer values. 5.64% is not the same thing as 6%. The second thing to note is this may be a different way to compute the mean because of the different scenario, but it is a mean nonetheless. The mean should be a value between the smallest and the largest. So we knew to expect a value between 3 and 9. We have 5.64, so that's intuitive. This is the way to calculate average growth rate. Let us look at another example where we will put in one negative growth rate, and we will also have more number of years. That way you will get to see, you will get to practice with the n so that you know it's not always a cube root, and you will get to see what happens if your variable actually experiences a negative growth rate. In our second example, we have 5 years, a 5-year stretch for our variable. In our first year, it grew 3%. The second year, it witnessed a drop in value, so fell 5%. In the third year, grew 6%. In the fourth year, positive growth rate of 7.2%. In the final year, it again dropped 4% in value. How do we compute the growth rate now? Our storyline still remains the same. We start with our $1. In the first year, our dollar grows 3% in value, so by the end of the year, it becomes 1.03 times what it was. Times 1, of course, means nothing. That's the advantage of starting with the $1. Then times, in the second year, our variable lost 5% in value. Something that loses 5% in value is worth only 95% of what it was. So in the second year, it becomes, by the end of the second year, this 1.03 actually has a value of 0.95 times 1.03 because it has lost value. So we start our third year with this value, gain 6%, so times 1.06. In the fourth year, we gain 7.2%, so times 1.072. In the final year, we drop 4% in value again. Something that drops 4% in value is worth only 96% of what it originally was, so times 0.96. Need the average growth rate over the 5-year period. So we have 5 years, so the fifth root of, this time we need the fifth root of this product. So fifth root of 1.03 times 0.95 times 1.06 times 1.072 times 0.96. Let us work this out. On most calculators, you will need to do the product and then need to raise this to an exponent of 1/5. That's what a fifth root is. 1.03 times 0.95 times 1.06 times 1.072 times 0.96 equals 1.0674. Then we apply the fifth root, so to an exponent of, open parenthesis, 1 divided by 5, close parenthesis. On an average, our dollar is worth 1.0131. So again, just like last time, if our dollar has grown on an average to a value of 1.0131, then this implies a growth of 0.0131, which in turn implies a growth rate. Now we need a percentage, which in turn implies a growth rate of 0.0131 times 100, or 1.31%. In other words, over this 5-year period, the average annual rate of growth was 1.31%. So to wrap it up, again understand the geometric mean is used in special scenarios. It is when you are averaging out indexes, percentages, ratios, or index values. It is applied when, this is the key thing here, it is applied in any scenario where you are looking at a multiplicative process evolving, unlike the arithmetic mean where there is an additive process that goes into the changes from one place to another. So this is how and when to apply the geometric mean.